100 kilowatts of heat. Off live AI chips. No fans, no spinning metal. Just a sealed tank of clear fluid boiling on purpose while whole servers sit fully submerged. Here is exactly how it works. Here is the problem air cannot solve. One rack of AI graphics chips now pulls 50 to 100 kilowatts, the draw of a small neighborhood. Blow air across chips that hot, and you stall out around 20 to 30 kilowatts per rack. Push past that and the fans scream, the power bill climbs, and cooling towers drink water. Cooling, not chips, now decides how tightly you can pack AI. Start with the tank itself. There are two ways to drown electronics in coolant. In the first, the fluid stays liquid the whole time. Pumps push it past the chips and out to a cooler. That is single phase. In the second, the fluid is allowed to boil right at the chip, turn to vapor, then condense back to liquid. That is two-phase, and it is what this video is about, because the boiling is the trick. Picture the setup. This is not a chip sitting in an open puddle with air above it. It is a sealed bath. A closed tank, lid clamped down, servers lowered in until every board is fully underwater. No air gap, no fans inside, no exposed fluid. The whole computer runs submerged. That should set off an alarm. Water and live electronics do not mix. One splash and you have got a short circuit and a dead board. So how does a running server sit soaked in fluid and not fry itself the instant you power it on? The answer is not the tank. It is what the tank is filled with. Meet the fluid. The stuff in the tank is not water and is not oil. It is an engineered coolant built to do one job: carry heat without carrying electricity. A fluid that does not conduct electricity is called a dielectric. That single property is why a live circuit board runs soaked in it and never shorts out. There is no path for current to leak through the liquid, so the board behaves as if it were sitting in dry air. The best known examples are fluorocarbon coolants, like the 3M Novik and FC72 families. Now the clever parts. Its boiling point is tuned. Water boils at 100 degrees Celsius. These fluids are engineered to boil far lower, somewhere around 49 to 60 degrees. Why aim so low? Because silicon starts to suffer above roughly 85 degrees Celsius. So the fluid is designed to boil off the chip well before the chip ever reaches its danger zone. Think about what that guarantees. The chip physically cannot get much hotter than the fluid's boiling point, because the moment it tries, the fluid touching it boils and carries the heat away. The boiling point becomes a temperature ceiling. But boiling by itself does not explain the number on the thumbnail. Why does turning liquid to vapor haul away so much more heat than just warming it up? Now the heart of it. Here is a fact that feels wrong the first time you hear it. Warming a gram of liquid a few degrees takes a little energy. But turning that same gram from liquid into vapor takes a huge gulp of energy, often 10 or 20 times more. That hidden energy cost of the boil is called latent heat, and it is the whole secret. Watch where it happens. Right on the surface of the hot graphics chip, a thin film of fluid flashes into bubbles the instant it touches the chip. Each bubble that tears free carries away a big slug of heat and floats it up out of the way, a process called nucleate boiling. Fresh, cool fluid rushes in to take its place and boils in turn. Boil, lift, refill, boil again, thousands of times a second across the whole die. And here is the payoff of the phase change. Because every bubble hauls off so much energy, the chip's temperature barely moves. It sits nearly flat, pinned near the boiling point, no matter how hard the AI workload pushes it. That is the real reason one tank swallows 100 kilowatts. It is not that the fluid gets hot and carries heat away in its warmth. It is the boiling itself doing the work. The phase change, not the temperature, moving the heat. So the bubbles rise full of energy. Where does all that heat actually go? Follow the vapor up. Every bubble climbs to the empty space at the top of the sealed tank above the fluid line. A cloud of hot vapor now holding all that latent heat. Waiting there is a condenser. A coil of tubing running across the top. Cool water fed from a loop that runs out to the rest of the building flows through that coil. When the hot vapor hits the cold coil, it does the reverse of the boil. It gives up its heat, turns back into liquid, and drips down as a gentle rain straight back into the bath. Nothing escapes. The fluid never leaves the sealed tank. It just cycles. Boil at the chip, rises vapor, condense on the coil, rain back down over and over. None of it gets used up. What actually leaves is the heat, and it leaves in the water. That water, now carrying the chip's heat, flows out of the coil to a dry cooler or a cooling tower on the roof, sheds the heat to the outside air, and comes back cold to do it again. So trace the whole chain. Heat from the chip goes into the vapor hands it to the water carries it outside. And not one fan turned to make any of that happen. So here is the full machine, end to end. 100 kilowatts pours off the chips, boils the fluid, rises as vapor, condenses on the coil, and rides the water loop out of the building. And not a single fan spins the whole way. That buys three things air cannot. It is near silent because there is nothing to spin. It is dense. You can pack racks tight since the heat has somewhere real to go. And the cooling itself sips almost no extra power. The energy overhead drops until nearly all the electricity goes to computing, and almost no water evaporates away. But it is not free. The tanks must be sealed and precise. The engineered fluid is expensive, and servicing a board means fishing it out of a bath, which operators find fiddly. Those costs are exactly why immersion is still niche. But as AI chips run hotter every year, that quiet boiling tank is spreading fast. So that is the one big idea. A controlled boil moves 100 kilowatts of heat that air never could. No fans, no drama, just a phase change doing the heavy lifting. Next, we will line up the two rivals. Single-phase immersion, where the fluid never boils, and direct-to-chip cold plates that skip the tank entirely. Which one wins? That is the next teardown.